So a few years ago, this image came out of a black hole, and we had been waiting a while to receive this image, and there was a lot of hype about it. You know, we're going to get this picture, this great picture of a black hole, and when it came out, everybody was like, "Oh, you know, is that it?" And it's kind of fuzzy. But this is actually an amazing picture when you think about all of the work to take a picture so many millions, billions of miles away, and to get it with this level of detail, especially of a black hole, because by definition, a black hole is something you can't really see. There's darkness because no light can get out of it. So in this video, I want to talk a little bit, give you an introduction to black holes and to wormholes, and talk about maybe why it's so hard to get, great images of some of these famous cosmological or celestial objects. Let's get started. So we start with the question, what is a black hole? Well, a black hole is defined as a place in space where gravity pulls so strongly that nothing can escape it, even light. Imagine gravity pulling so hard that light can't escape. So when do we get black holes? We often get a black hole when a star collapses, one of these super giant stars, and dies. Then we might get a black hole as well. So why can't we see them? I've sort of alluded to this earlier. We can't see black holes because no light can escape. They're invisible. So this is obviously an artist's rendering. This is not a real picture of a black hole. We'll go over the different parts of this, but black hole gets its name from the obvious center where no light can escape, so it appears as darkness. We can't see black because it does not reflect any light. So how big are these things? Right, let's get a sense of scale. Small, large? Well, it's actually both. Some black holes are very small. Others are massive. So let's go over the difference. I've made a little scale here. Some black holes, scientists hypothesize, are really small. We might call those micro black holes, and they could be about the size of an atom, right? So what would that look like? Well, again, it'd be hard to see. It's a black hole. But it would be something super tiny, but with a ton of mass, right? A black hole has to have so much mass that it has, therefore, gravity that's pulling in the light. Okay, so they can be small. They can be what we call stellar black holes, which is about, up to 20 times the mass of the sun. There are probably several of these in our own galaxy, the Milky Way galaxy. So think of these as kind of in between, right? But still pretty big, right? They're stellar, about 20 times the mass of our sun. And then, of course, the ones that get the headlines are the supermassive black holes, where their mass is more than 1 million suns, okay? In fact, there is some evidence that there is a supermassive black hole in the center of every galaxy. We're pretty sure there's one in the center of our galaxy, Sagittarius A, the black hole in the center of our galaxy. And there's some evidence to say that there's a supermassive black hole in the center of every galaxy. All right, so sense of scale there. They can be tiny, they can be pretty big, and then they can be really big. So let's talk about some of the characteristics of a black hole. Black holes have a few things, a few characteristics, which it's probably pretty important to understand. So if this was the black hole, I know it's gray, but imagine this was our black hole. This outer edge is called the event horizon. And that's basically just a boundary in space-time through which matter and light can pass only inwards. So when we're out here, light can pass and go in lots of directions. Past the event horizon of a black hole, light can only go in that direction. Okay, Then we also have singularity. Singularity, often towards the center, is a region where space-time curvature becomes infinite. So this singularity in a black hole is bending space-time so much that it has infinite density. Well, we know gravity then is affected by this infinite density. Therefore, everything is being pulled in. So, when I say bending of space and time, what I'm actually talking about is if you're imagining space and time together as sort of this grid pattern, we know that these massively large objects like the Earth, like the Sun, like a black hole, actually bend space and time. And my example, if you watched my other video on the multiverse, I kind of gave a very similar example. Imagine you are on a trampoline and you are towards the center and you're sitting in the center and you're pretty massive, let's say. Anything that is on the outside, all right, you put a soccer ball, a tennis ball, or I don't know, a drink, you're drinking a Coke Zero, let's say. You sit it here. Well, if you're sitting in the middle, everything's going to move towards the center, right? Because you've bent the fabric of the trampoline. Same thing happening here with super large, massive objects. The bending of the fabric of space and time causes things to naturally be drawn to it or towards it. Okay, so let's talk about some characteristics of a black hole. So obviously, the most famous part would be the shadow, the black hole shadow, right? That's in the center. And again, this is an artist drawing. This is not an actual picture. Right around the black hole shadow is a photon ring. A ring of, if you think photon, right, it's just a light particle. Then as we move out, we've got something called Doppler beaming. If you know of Doppler, the Doppler effect, that's like if you hear an ambulance coming towards you, right? And then it changes, right? It's just the sound being shifted. Well, actually we have Doppler in the shifting of other properties as well of these black holes. Then the big thing that you can see, and it's estimated that, 1% of these supermassive black holes have this accretion disk. And this is just this disk of floating gases and dust that's actually been compressed so much that it is actually kind of glowing to some extent because it's being heated up so much on its way towards the black hole. Okay? Then, of course, you could have the far side of the disk and the underside of the disk. Remember, these are three-dimensional objects, so it's kind of hard to show that in an artist's rendering. Okay? So that is a general overview of the characteristics of a black hole. Okay, so let's go into a little more detail about the event horizon. Okay, so the event horizon, remember, is that point by which nothing can escape. So general relativity, all right, think Einstein, tells us that massive objects like a black hole, like the Earth, like the Sun, deform, bend space and time. So this was the example I gave you, right? So we got space and time here, the object bending it. Well, in black holes, the event horizon, space-time is so deformed, right? It's so deformed down that nothing can escape. And in fact, one of the most interesting points about the event horizon in black holes is that the closer you get to this event horizon, the more time dilates, right? Clocks actually tick slower. Time changes at the black hole. So I got a few little examples. All right, so here's our black hole over here, right? Here's the event horizon. If there's a little space between the event horizon and the black hole, light, anything can go in all directions. See all the directions it's going. Now, the farther we get, or the closer we get to the black hole, notice that, light can still get away, but notice that most of these are now pointing towards black hole. right? There's so much gravity, there's so much pull that even the light is being pulled here. And then anything, of course, past the event horizon, you would never see because the light from it only would go inward. So past the event horizon, we cannot ever see what's in there because it will never emit any light that we can see. The light can't escape. So it's black, it's dark. All right, so another really interesting phenomenon of black holes, something called Hawking radiation. Stephen Hawking, famous scientist, proposed that black holes do actually give off some thermal radiation at certain temperatures. So we call this Hawking radiation after the scientist. So what it's actually saying is it's actually giving off some radiation, some thermal radiation. Well, if you think about the laws of our universe, if a black hole is giving parts of itself off as radiation, then that means the black hole over time will be shrinking. Now, we're still talking about, millions of mass of the sun. So these things are huge. But if this Hawking radiation hypothesis is correct, black holes will actually be shrinking because it's giving off this radiation. Okay, so the question that everybody always wants to know is, what happens if you fall in a black hole? Okay, so there's the black hole. There you are. I don't know why you're out there, but let's say you're, on a little trip and you stumble across a black hole. Well, once you pass the event horizon, right? Event horizon, you are going to be carried to the singularity in the center. At that singularity, right, this is where it gets a little gruesome. You're going to be crushed into an infinite density, right? You're something that's so super dense. In fact, it's infinite density. And then that mass will be added to the mass of the black hole. You will become part of the black hole. Okay, so I think the bottom line here, moral story, is we don't need to be getting too close to these black holes. Oh yeah, there you go. I animated that a bit. Once you get in there, then your mass disintegrated. All right, so we talked about black holes. What about wormholes? Well, a wormhole is really also known as the Einstein-Rosen bridge. You can imagine who came up with this idea. It's basically just a hypothetical tunnel connecting disparate points in space-time, right? So we hypothesize that there's some tunnel that's connecting these different points in space-time. This is actually very consistent with Einstein's theory of general relativity. So what might something like this look like? Well, a wormhole would connect two points in time. So here's a point in space-time, here's a point in space-time. A wormhole might connect those two. So what are some things literally that it might connect? Well, it might connect a short distance. It might be just a few meters. You might take a wormhole from here across the room. Or it might be a long distance, billions of light years away. It could also, perhaps, connect different points in time, right? If wormholes are kind of here in this bending of the space and time, maybe it's actually connecting to a different point in time. And scientists hypothesize a lot that perhaps a wormhole could take us into the future. Going into the past might be a little more challenging, but the future, many scientists think perhaps is an option. Different universes, right? We talked about this in my other video, if you watched that, about the idea of the multiverse theory and how a wormhole could possibly connect different universes. Okay, so kind of crazy to think that these things might be out there. They are certainly hypothesized. Many scientists think that they are something that could be real. So a wormhole is basically just a tunnel connecting two different points in space-time. And this is what I just mentioned. If you watched my video on the multiverse, this sort of takes that a step further. Is our entire universe in a black hole? And is that black hole really just a tunnel or a wormhole to another universe? And then our universe might be hidden, or other universes are hidden because light can't escape that black hole connected by these wormholes. Okay, so black holes, wormholes, multiverse, it's all really fascinating, very theoretical. We know black holes exist. We can see them, we take pictures, but these wormholes, the ideas of different universes, that's just something really to get some more research on and really look into. So hopefully in this video, it helped you understand a little more about these cosmological events, these really fascinating celestial objects called black holes, and the theorized wormholes.